Welcome to ETAP webinar, a realistic approach and new insight to protection and coordination analysis, introducing StarZ. I'm Mohammed Zadeh. I'm the manager of T&D Protection Division at ETAP. In this webinar, first I will introduce challenges of setting modern protective relays. We look at today's microprocessor-based relays, their settings, functions, and interfaces. Then we discuss about the NERC report, pointing out that there is a considerable human errors in setting protective relays, which eventually results in loss of reliability. We look at NERC recommended solutions and how ETAP StarZ can be utilized to minimize such errors. After that, I would introduce StarZ module, its philosophy of operation, key features, and how it can minimize setting errors and study times. We also discuss the relay library that would be available for the first release. I would like also to emphasize about ETAP Software Foundation and how it can make a remarkable difference in performing power system studies and user experience in regards to a StarZ software module. We will have a quick demonstration of StarZ various features and tools, and finally I will summarize the webinar. Today's microprocessor-based protection relays offer many functionalities. However, they require large amount of settings and complex scheme logic to be operational. Multiple settings groups are available to adapt protection settings to different system configurations. Many protection elements are provided for different applications. Relays communicate that are interlocked to other protective devices to exchange protection and control information to enhance and accelerate protection and control system performance. Relays also have become very flexible while requiring extensive customized scheme logic to be set by user to be fully operational in practice. Here is an example of a distance relay including several protection elements such as distance 21, over current 1551, under voltage 27, directional over current 67, and many more. Each protection element may have plenty of outputs. As you can see in the far right table, just Moho ground distance element of this relay has 20 outputs. This offers significant flexibility for the user while it makes it more complicated to pick the right element outputs. Most of today's high voltage transmission lines incorporate one way of communication aided schemes to reduce trip time as well as increase the reliability of protection system. Some relays provide built-in functions to take care of required logics, and some leave it to the user to develop their own logic. This also adds to the size and complexity of relay scheme logic. There are several applications such as series compensated lines, double circuit lines, isolated and compensated distribution systems, and many more where the protection settings should be adjusted based on system configuration. This also adds another level of complexity by utilizing multiple relay setting groups and manual and automatic switch among setting groups. All aforementioned complexity in relay settings open a door for human errors and eventually protection system maloperation, even though relays are extensively tested before and after installation in the field. As recently reported by North American Electric Reliability Corporation (NERC), based on the protection relay misoperation data collected from January 1, 2011 to March 31, 2012, 28% of misoperations is due to incorrect setting and logic error. If you look at this kind of a blue sector here, that's 28%. Human errors in relay settings and logic could not be found as relay testing using common test kit is limited and does not simulate or test all possible scenarios. Several solutions have been proposed by NERC report, including peer review, increased training of protection engineers who set and test relay, more extensive fault studies, standard templates for setting and scheme logic, and also a periodic review of protection settings when there is a change in system topology. ETAP is offering a solution called StarZ, which helps to perform most of the recommended solution. Having actual relay settings and protection function in a simulation environment could simplify the peer review process and make it more effective and efficient. Simulation environment to set and evaluate protection function and scheme logic is an effective tool also to train protection engineers. Utilizing a software solution, user can perform extensive fault or load flow studies and evaluate protection settings and protection coordination. User can easily review protection system performance if there is a change in the system topology in a detailed and more realistic simulation environment as well. So with that introduction, let me introduce you to ETAP StarZ software module. So let's start with this first question, that what is a StarZ? So ETAP StarZ software module is a comprehensive tool to effectively simulate protection system mainly at transmission and distribution levels, but not limited to that. Behind the StarZ user interface, there is an intelligent and powerful engine which allows to simulate and evaluate model-specific protection settings and functions similar to the actual relay. This means that, as we will see in the demonstration and later on in this presentation, that in ETAP, user encounters with the same settings and protection element outputs of the actual relay. Also, the model relay in ETAP performs similar to the actual one for steady-state analysis supported in this module. User can also set and simulate scheme logic, relay interlocks to other protective devices, relay communication on top of the existing protection elements. In addition to model-specific relay models, ETAP provides a generic model which can be utilized to simulate general distance protection function for system analysis where a specific model is not required. Intelligent tool is provided as part of the StarZ to assist user to identify setting errors and fix them. Basically, if we are dealing with a large number of settings, protection elements, and logics in the actual relay, and we are trying to simulate the same settings, elements, and logics in a simulation environment, we are dealing with a complex modeling. So, in order to simplify and reduce the human errors in modeling the protection system, we have provided a tool to assist user to identify the main, basically, settings errors in the modeling of the protection system and help the user to fix them. StarZ also generates various result plots and reports for performance evaluation and setting verification. So this simulation tool ultimately reduces human error in relay settings and logic, and also minimizes the time required to perform protection and coordination study. For those that are new to ETAP, STAR is the software module that is used widely in industry for overcurrent protection coordination for many years. So StarZ is its new sibling, which inherits STAR functionality to evaluate overcurrent protection devices, while it supports also impedance protection. So Z stands for impedance protection. That's additional functionality to STAR that is incorporated as part of the StarZ module. Let's quickly review StarZ key features. I will later on go through each feature in details during demonstration. The most key feature of StarZ is its capability to simulate model-specific protection settings and functions. So let's quickly take a look at that and see what does that mean. Here is an example of GE D60 distance relay. As you can see, the settings that users face in ETAP in the left hand side, you see the settings in the ETAP relay editor match the same settings in GEUR setup, which is a software to set GEUR relays. As you can see in the ground distance element, we are in the ground distance, we have function, we have functions. If here is a drop-down list with the enable disabled settings, you're going to have a drop-down list with the enable disabled. So same settings, same ranges, same labels. Even same order of the settings as well. So direction, direction, shape, shape. Zero sequence compensating factor in the same way that the manufacturer asks for the settings with the same ranges, defaults, labels, you see with the same thing in the ETAP side. Let's look at another example. This is the ABB REL 650 distance relay. As you can see, we are looking at a MOHO distance relay, and we are comparing to the relay settings in the manual. So you see that the operation on, you have operation on and off, and the default could be off. We set it to on for testing purpose. You have the zero sequence compensating factor, which is totally different than what you saw on the GE. So it's K and Mac 1, K and angle 1, line angle, zero sequence for zone 2, the minimum current for operations for phase and ground, and you see the same settings, same ranges, default values in the ETAP side and in the manual. Now the settings are the same. Now let's look at the output of the protection function. So again, we are dealing with the model specific protection functions. Let's look at the GE again, D60 relay. We are looking at the element outputs, protection element outputs. Here I have ground distance zone 1 operation. You see here is the same as the one in the GEUR setup flex logic, GND distance zone 1 operation. You have GND distance zone 2 pickup. You have GND distance zone 2 pickup. So you see the same labels for the protection element outputs in ETAP and in the GEUR setup. Now let's look at another example in ABB. So in ABB I have for MOHO, Z-MOHO distance relay, TRZ trip zone 3. You have the trip zone 3 here. Again, ABB is a functional block, so they only have labels per block. So the left label means that's the block, and the right hand side is the element output. So you have trip Z3 and let's say trip, and you see the same trip Z3, and as starting trip zone 1, you see the starting trip zone 1. So again, same protection element outputs in ETAP as same as the one that you see in the relay manual or the relay setting software. ETAP 17 will be released with 40 plus relay models from various manufacturers such as Schweitzer, GE, ABB, Alstom, Schneider, Siemens, ZIV, Aerophase, Arctech, and Toshiba. We are providing the distance, directional, load encroachment, overcurrent, and overload functions for these relay models in the first release of StarZ, which would be ETAP 17. There will be also a generic distance relay model that can be customized through Relay Editor to simulate other generation protection relays. We also provide 500 plus non-distance relay for ETAP 17. Before doing the demonstrations, I would like to also emphasize on the ETAP software foundation. First of all, ETAP is an integrated suite of power system enterprise solution that spans from modeling to operation. Also, ETAP software meets the rigid standards for quality and safety established by US and international standard bodies for nuclear facilities. Some of the largest firms in the industry rely on ETAP to ensure the highest possible project quality and manageability. ETAP software has been used by various industries, and this means that the ETAP has done the diligent job to ensure that we have provided intuitive user interface for power system simulation and operations. We have 50 plus modules, including the basic ones like load flow, short circuit analysis, harmonic analysis, and then we have transient stability, contingency, voltage stability, and optimal power flow analysis. ETAP supports AC and DC systems and unified load flow analysis. This actually is a great feature for modeling the new generations of the microgrids and renewable energy resources which integrate into the DC and then from DC to AC systems. ETAP supports series compensated and coupled lines, static VAR compensators, high voltage DC transmission system, and renewable resources such as wind and solar. ETAP integrates with a real-time application. This means that ETAP can communicate with the various protocols to acquire real-time information from the field and adjust the circuit breaker configurations, loads, and voltages in the system and utilize the real-time value to perform analysis. ETAP also supports geospatial electric diagram for distribution systems, as well as supports elements and modules for railways, marine, and aerospace applications. So with this introduction, let's start doing the quick demonstration on StarZ. Let's have a quick demonstration. So one of the first feature that user encounters in ETAP is the way ETAP manages graphical modeling of the protection system. So number one is that a user can utilize composite networks to model the details of the substation. As you see here, in this side I have two transformers connected to two transmission lines in a substation. So if I go inside this composite network, I see all the details of breaker and a half configurations with all the protective devices, circuit breakers, current transformer, voltage transformers. Also, for the ease of clarity, we also have the remote connector to minimize the amount of wiring that crossing each other. User can also utilize composite network to model piece of the protection system. For instance, here I've used a composite network to just put the bus protection because it has lots of connection to the current transformers. Also in ETAP you always can have multiple presentations of your system, so you can go to your study view and in a study view, basically you hide most of your protective devices or all your protective devices if you're just intend to do basic studies like load flow or short circuit. But if you're intended to do the protection studies, you can actually unhide all your protection devices in a different presentation and use that presentations for the StarZ analysis. Now let's take a look at the relay model in ETAP. So as you can see here, I have a relay element which is graphically connected to the current transformers and voltage transformer. In this case, my voltage transformer is connected through the remote connector for clarity. Now, if I go inside the relay, I have multiple tabs. In the input tabs, basically we do the wiring between the terminals and the available current and voltage transformer to the relay. So relay can have multiple current terminals for phase and ground, multiple terminals for voltage. Now the number of the terminal depends on the relay model. So for instance, in case of the, let's say, let me see if I can find the StarZ relay, it has only 2 current inputs, while in the case of the G relays, it has 3 current inputs and 3 voltage inputs. Now, a user can assign the current transformer. Here is a breaker and a half configuration. So I'm assigning the 2 CTs, and I have 1 VT. Now I can leave them empty here if I have just one voltage, that's one voltage source used. A user can define multiple digital inputs, so it can bring the status of the other protective devices or the relay outputs. User can also do the logical assignments of the terminals to the source. Source is available for specific relays depending on the model and manufacturer. So where user can do a logical summations, let's say, of the terminals. For this case is a breaker and a half configuration. So I can add up the currents in this case for the phase source. Now relay, we define the inputs. Relay can have multiple outputs. These outputs represents, let's say, the contact outputs, the digital communication signals that's transferred from the relay to other protective devices. In this case, the trip is defined through the scheme logic. Then we have the settings for the overcurrent and overload protection. We have the settings for distance protection. We talked about the distance protection, that all the settings are the detailed. So as you go from one relay to another relay, let's say in this case the ABB relay, all the settings are different. All the categories or settings are different than the one in the G relay. We have multiple settings group. User can utilize these groups to implement different settings for different configurations. And also we have a setting base. If the relay is secondary, you're gonna see secondary. If the relay is primary, you're gonna see primary. And if the relay has both, you're gonna see both, and you can choose which one you would like to set the relay base. Now, in the scheme logic, user has the access to all the protection elements of the relay, digital inputs, timers, latches, control variables. The interior variables you can define for the ease of use in the scheme logic to make it more readable. And also the outputs of the relay are available, so you can assign, for instance here I've assigned the trip from the MOHO and quad characteristics for all the zones to the trip output of the relay. So with this you can see that the relay actually is set and is interfaced very similar to the actual relay. Let me show that when I was talking about that, when we are dealing with a complex relay and you make some mistake in the things in the relay, what's going to happen. One aspect of it is that if you make some mistakes in the relay logic, let's say you put a wrong protection element here, something like that, what's going to happen is that we have a logic validation or error check that tells you that the variable name that you use here is not valid. Now let's create a quick StarZ view for the relay L1 time here and see how simple it is to create a StarZ view and look at the RX characteristics of this relay. So let me uncheck the phase elements and also the load encroachment. Now you can easily go ahead and add the remote branch, the longest branch connected here for 40 ohm. So I have my zone 1, zone 2, zone 3 ground distance element. I can also plot the zone 4 if I'm interested. There you go, I have the zone 4. These characteristics are generated out of the relay equations and logic. If you go ahead and enable and disable something in this case, so let me go ahead and do that. Let's go to the ground distance zone 1 and disable zone 1 in this case and press OK. So what's going to happen? The zone 1 disappears. So if you come here for the first time and you don't know what's happening, why zone 1 is not shown, and you go here, it says characteristics not plotted. We have a tool called alert view in a StarZ view. So if you go here, it says that characteristic not plotted for the selected protection relay zone 1 may be disabled in the relay settings. So that's a very good clue that the settings for zone 1 is disabled. So if I go to the ground zone 1 and say disable, I can place it or enable. Now, if the characteristic shape is selected wrong, so instead of quad is selected moho, you can easily see the moho here and you can figure out my characteristic type is wrong. So let me get back and put this back to the quad. Another thing that is really important here is that let's say in this relay, I go ahead and disconnect the CT. Basically, I say that there is no CT for this relay. So what's going to happen? All the characteristics will disappear. And you may wonder why. You go to the alert and it tells you that the phase CT not specified and characteristic is not plotted due to an invalid impedance ratio. So it gives you some clue that what's going on with this relay. So I can go ahead on this relay and go to the input and assign the right CT. So if the CT is not properly selected, or if the setting is disabled, enable, or something is wrong in the setting, you can easily figure out here. Another thing that can be done is that if you have already done some analysis, run the fault analysis on this distance relay, which I've done it already, you can link it to the report of that relay. So what it does, it shows the status of all protection element outputs and also the operating time for different protections. So in this case, you see that zone 1 operates in 1 cycle, zone 2 is 300 plus 1 cycle, and zone 3 is 750 milliseconds per 1 cycle. So in this case, I can go ahead and also plot the scene impedance as well in this case. So I can go ahead, and as I move the sliders for fault location, you see here that the scene impedance is moving. So I can go ahead as well and enable the settings, so you can see also the scene impedance value and the scene impedance value and scene impedance location as it moves with time. So you have scene impedance per zones or per elements separately, because different elements may use, not always, but may use different mechanism to measure the scene impedance, and they may have different zero sequence compensating factor. So if you put a different zero sequence compensating factor, you will see that the scene impedance would be different in these cases. Another thing is that you can, for each relay, you can go ahead and plot multiple relays. So in this case, I have prepared StarZ view with 2 relays, that is one from GE and one from ABB relays. As you see, I have zone 1, 2, 3, 4 plotted for GE relay and zone 1, 2, 3 for the ABB relay. And my plot right now is in primary. I can go ahead into the plot option and change the plot from the primary to secondary with respect of any of these relays. So I can go ahead and change that. Now you see that the axis is changed to the ohm secondary and the values actually drop, and you can also see the impedance ratio as well here, that is actually 0.1. Now that I have my characteristics setup. I'm sure that my settings for characteristics are correct. Some of the time delays for zone 1, 2, 3 could be also checked through the StarZ view. But I can go ahead and do some analysis on this system. So there are three options available. So you can do a single fault, you can do load flow, or you can do sliding fault. Basically, in single fault, you can apply fault anywhere in the system between the connector. Load flow, you can run just load flow to make sure that there is no maloperation during the normal or heavy load condition and check your load encroachment element. And in case of a sliding fault, you can select a transmission line. Let me just select L1, and you can vary the fault location and fault resistance within some range. So fault location, you just determine the step, and locations, you determine your fault type. If you have a series compensated line, you can actually say, I want to simulate my metal oxide varistor in this case. One thing that is important here, once I run this fault analysis, it's going to run multiple fault analysis at the same time and evaluate the protection relays as actually selected. So in this case, I've selected the two lines across this transmission line. So if I run this analysis, okay, now I have the result. You see that the fault currents and voltages are shown on the screen. You can go ahead. We have provided various display options to change the values, sequence values, or phase-to-phase values. You can see those. You can move the fault location and see the values, how they're changing. What can be done at this stage is that we have various tools to verify the results. The first thing that I would recommend the user always to check to make sure that there's nothing wrong is we have something called message viewer. So this message viewer, if something is not right, it's going to tell the user that something is not right. For instance, let's give some try here, is that if I don't select the CT here and run the analysis, what's going to happen is that it's going to assume a zero current for that CT, and probably the relay is not going to operate, but is going to inform the user in the message viewer that something is wrong with this relay and the current is assumed zero. So go back and take a look and fix that. So if I go to the message viewer, it says that relay input voltage terminal say is not assigned. Zero current assumes for IP1 in the analysis. So that means that I have to go back and fix the CT assignment. So another thing that can be done is that go ahead and change the CT rating to 0. Or if there is something wrong in the scheme logic, let's say I go ahead and put this trip 5 which does not exist. First of all, the scheme logic by itself tells you that there is something wrong, but if you decide to close and ignore this message and try to run this analysis, message viewer is going to catch that issue and tell you that something is wrong with running this analysis. So in this case, if I go here, so what it says that, first of all, it says that the relay L-atom has assigned CD current rating primary and secondary is 0. So we're going to fix that. The CT is wrong. And then the scheme logic variable T5 is not defined. So the protective device, the L1 tom, is actually skipped from the analysis. So let's go ahead and fix both issues here. This should be 1000 ampere. And also the scheme logic for this relay is going to be trip 5. So we have very powerful and intelligent tool to find issues in your model relay interfaces and catch them and show to the user that how to fix them. So that is a great tool when it comes to the detailed modeling of the protection relays and protection and coordination studies. Now let's look at some of the other ways to look at the results. One of the great tools that we have is called the plot manager. So plot manager is a tool that can connect to any studied report and visualize or create some plots out of the study results. So let me bring here the plot manager. So plot manager shows the studied reports. So I'm connecting to the L1LG report that I just did. I'm selecting the relay at a tom substation, and I'm having 4 zones and the trip signal selected. And at the 0 fault location and 0 fault resistance, let me plot. So as you can see, I have zone 1, zone 2, zone 3 time state plot. So it shows that how each zone reacts to the fault. And zone 4 does not detect the fault because this is the forward fault. And relay is set, zone 4 is set to the reverse direction, and trip signal which comes out of the 3 zones, as it shows that it trips in 1 cycle. Now, one of the great things about the StarZ plot manager is that you can go ahead and create a time distance resistance plot out of your final trip signal. So as it is shown here, it's going to create a graph that shows the full spectrum of fault resistances and fault locations. So what this graph tells me that my relay is protected up to 80% for lower fault resistances, but as the fault resistance increases, relay is going to go to the zone 2 and zone 3. So basically in one shot you can figure out that if your zones are kind of correctly set, and also if the trip times for each zone is correctly adjusted, and the relay logic is also correct because trip comes out of the relay logic. So this would be a great tool actually to figure out if something is wrong with this relay. Now let's look at another case that I've created here. Is that if I go to the revision POTD, I've created a relay settings in which that relay at 2 ends of the L1, relay at L1 Tom 230, and relay at the Weber substation here, L1 at the Weber substation. These two relays are going to talk together and implement a POTT scheme. So if I go to the relay settings here, in the outputs, each relay has a trip signal that trips the circuit breaker, and also it sends a transfer trip signal to another relay. So we have a logic for the POTT implemented in both relays. So if I run this analysis and also go to the plot, let me just close these old plots here I have and go to the next to the L1 LG POTT. I've done this analysis before, and I go actually to the L1 Tom and go to the trip signal and plot the trip signal in this case. Now what you would see here is that up to 100% of the line is protected in the first zone because two relays talk together to improve the speed. So the 100% for lower fault resistances, 100% of the line is protected by the first power system cycle, and as the fault resistance increases, still the operating time is within 1 cycle, but if the fault resistance goes beyond that, it's going to go to second zone or the third zone operations of this relay. So this is a very good way that in one shot you can figure out through the time distance resistance that if there is something wrong with the relay settings, time delays of the zones or characteristics, and as well as the logic of the relay. One more thing that is also important to emphasize is that since in ETAP relay behaves the same as the actual relay, here what you see is kind of the dynamic behavior of the relay. So you see that as the fault resistance increases, the reach of the relay actually reduces, and you will also have the in-feed from the remote, and that also impacts the performance of the relay. The other tool that we have that I would like to also quickly demonstrate is called the sequence of operation viewer. This tool looks at the relay as a black box, so it doesn't care what is inside the relay. It only cares about the outputs, inputs to the relay, and also the interlocks with the circuit breaker. So in this case, you see that for a simple case that fault is at 0%, and 0 fault resistance, the relay at the Tom substation trips in 1 cycle, and it trips the circuit breaker in 100 milliseconds, while the relay at the Weber substation, it trips in the second zone. Now, if I increase the fault location, you see that now at the
30% fault is within zone 1 of both relays, so both relays are going to trip immediately in one cycle. Now if I get closer to the other side, actually the relay at the Weber substation is going to trip immediately. You can see the impact of fault location, fault resistance, which relay is operating first and second. Also for the case of a POTT, also I can show you that you can see all the communications between the two relays, that when the fault happens, relay at a substation Tom sends a trip signal or receives a trip signal, relay at the both sends and transmits signal, and relay at the Weber substations also sends a signal because sees the fault also in the second zone. So relays talk together. All the interaction between the relays and circuit breaker trippings are also available in this view. So that's also a nice thing to show the events, that what happens in the power system in a higher level. User can also go ahead and create a report out of the setting of the relay. So in this case, let's say I have a Weber relay. I can go ahead and say that give me the report of the setting. So there are two options available. We can create Excel or XML file. So if I press OK, so this is going to basically create a XML and Excel file. Now if I go to the folder here, I have the Excel, and I think I have the XML as well. So let's look at the Excel file here that I have for the L1 Weber POTT. So if I go here, it creates a nice Excel file with all the relay inputs, output, distance relay settings, and also the scheme logic used for this relay. Now if you're interested to look at the XML file also, we have a ETAP XML format for this relay. If you would like to somehow utilize the data, you can take the XML file here with all the relay settings, overcurrent and distance, and use that for any data exchange that you would like to do. Also, user can also create a report out of the analysis results. For instance, here I can create a report out of the protection element outputs. So ETAP is going to create a crystal report where for this case it shows all the protection elements in time, their status, their primary and secondary scene impedance and impedance ratio. So user can print this reports and attach to the study reports and provide those to their customer. Let's summarize this webinar. So the main objective of ETAP StarZ module is to help the process of the protection settings and coordination, and ultimately reduce the human errors in relay settings and logics. To achieve this objective, we have taken the approach of doing the model specific protection settings and functions. But the key importance here is that at the same time that the model is very complicated inside, and the engine is complicated inside, but we have provided an intuitive user interface that user can simply feel the same environment as setting the actual relay. User can do scheme logic, relay communications. User can plot coordination characteristics and scene impedances, which are RX plots. The key feature of this RX characteristic that is linked directly to the settings and logic of the relay. So not only you see the characteristics based on the settings, but if you have a problem or errors in your logic of the relay or in your interfaces of the relay, the characteristics is not going to be shown, and it's going to declare that what's the issue. So we are using a very accurate and advanced load flow and fault analysis that works for the unbalanced network. It supports series, compensated, and coupled lines. It supports HVDC, SVC, and all these complicated elements in power system. This tool generates various plots to validate relay settings and scheme logic, especially the time distance resistance plot that we showed in one shot can tell you that if the relay is and relay settings and the logics are properly set. As part of the StarZ mode, we are providing an intelligent tool which let the user know if there's any mistakes in relay modelings in the settings as far as the interfaces or fundamental settings like enable, disables of the settings are concerned. With this, I'm done with the webinar. If you have any questions, please contact us. Thank you.